All right, I'd like to welcome you to this MAPS event today. MAPS, Modesto Area Partners in Science, we typically have about 4 talks each semester. And we have 2 more left, Friday, November 18th. We're going to have a talk about the monarch butterfly. And there's also going to be an art contest for K-16 students. And we're going to have our last talk Friday, December 9th. And it's going to be on microbes, medicine, and money, biomanufacturing in the 21st century. And next year, in the spring semester, we're going to have, we have 1 to be announced, so we are going to have 4 talks again. And this talk right here, so we have a talk about astronomy and physics. This is the physics show. And where was the auditorium that we had this before? The State Theater? Yep. So they're going to have liquid nitrogen. They're going to get a bed of nails, right, with a sledgehammer. So great demos that sometimes I do in some of my physics courses. And this is going to be a really good show there. And this is for all ages, this show here. And we have a couple of other talks about, one about climate change. And I can't even read this.
We don't know what she's talking about yet. Probably mastodons.
Okay, I see an elephant relative there.
So Dan, can I just interject
Go ahead.
quickly? The art contest, if you're interested in participating in the art contest, that will go along with the our next talk on November 18th. You can submit any artwork that you'd like to, if it has to do with monarch butterflies or nature in general, to the Great Valley Museum before November 11th. So there are some, guidelines for the size of the piece of work, but there are also signs around campus. So that way, if you're interested in doing something like that, then look for those signs on campus. Get your art submitted to the Great Valley Museum, which is on the first floor of the Science Community Center right next door to us. And then on November 18th, when you come to the MAPS presentation, your art will be on display. We're going to have a reception, an art reception in the Great Valley Museum lobby area that same evening. And then the talk on the physics show, we've done it at the State Theater before, but this year it's going to be in our auditorium, and that's over on the East Campus, and so that's in February of next year. So for the physics show, we're bringing it home. We don't need the State Theater anymore. We've got our own beautiful theater.
And they actually do bring a crowd. It was quite full over at the State Theater. And we do have our Science Colloquium series. It used to be every week, but now it's more scattered. But those Science Colloquiums are Wednesdays, 3:15 to 4:15 in the Science Community Center over there at room 115. And this is a great talk again for astronomy. Our NASA ambassador, Tom Crane, is going to give a talk about the sun. And so we have a lot of astronomy things going on. And next month, the first Friday of most months, we have our Great Valley Museum Telescope Nights and Science Nights. They have planetarium shows, which you can purchase tickets for. I think it's $1 for students, $5 for the public. And the telescope viewing is free. You can just come for the telescopes. And on the 4th floor, we're going to have probably about 6 12-inch Dobsonian telescopes. So they're about this tall, 12-inch mirror for the aperture. And we also have this 28-inch telescope that And it's going to be a full moon, so we're going to lose the deep sky objects like the Ring Nebula and Andromeda Galaxy and a few other objects. However, Mars will be available to view, Saturn. How many people have seen Saturn through a telescope eyepiece? All right. I see some smiles too. It's pretty cool, right? So we'll have that, and Jupiter will be up as well. So hopefully Jupiter's high enough where I can get the big telescope there and just have it on Jupiter and Saturn the whole night. We have Saturday, November 12th, 10 to 3, the Salmon Festival in the Knights Ferry Recreation Area. And this slide's useless now because we can't go back in time. So there was planetarium shows today about this topic, dark matter. It was a great show to see. I believe tomorrow the Great Valley Museum is hosting, what time is it, like 10 o'clock in the morning?
I think it was 10:30.
10:30, like around that to what time? Like in the afternoon? Yeah, but they're having, I believe they're having, I saw that they're having laser shows as well. So I think they have like a Halloween, like laser type show. From what I remember, I think there was like a Rocky Horror Picture show, one of their songs in that set there. And this is over too, so I know a lot of people went to the spooky night tonight. I think this is the last slide. So I would like to introduce our speaker, Professor Anna Nierenberg. And let me get, so I'm not going to spend a lot of time introducing her. And also, it might be interesting at the end for people to ask about her pathway to doing research in astronomy and physics. So I know I have a lot of astronomy students. They always ask me, well, I'm interested in astronomy. Like, what do I do? Like, how do I go advance my astronomy degree? And what do I tell them? Take physics. Yeah, people don't like that answer. Right?
Sorry.
Physics, math, and computer science, all those really important. But Anna got a bachelor degree, so that's UCLA, correct? And UC Santa Barbara for her PhD. And I'd like everybody to welcome Anna Nierenberg.
See if I can get this.
So you,
Am I being amplified? Oh, there we go. Hey.
so it's just the one you had open, right?
Yeah.
So should be good. And
Thanks.
clicker.
So thanks so much for coming. I love talking about my research and dark matter, and it's super cool to come to this campus. I've never been here before. It's huge, and there's a telescope. It's a really cool place, so it's a cool opportunity for me. I'm going to talk about my research using the James Webb Space Telescope to try and learn about dark matter. The first part of my talk is just going to be explaining what we know about dark matter, why we think it's there. And then I'm going to talk a little bit about how the James Webb Space Telescope will help us measure dark matter better than we have before. I'm going to end with some images that we just got last night from the James Webb Space Telescope, the first images of my program. We haven't been able yet, obviously, to do the full scientific analysis for the dark matter, so this is more of a teaser trailer for some results which will hopefully be coming out in the next year or so about dark matter from our group. And then don't hesitate to ask questions, please, during the talk. Okay, so I think it's very easy when we take our classes, when we listen to popular science, to get the impression that we have a pretty good understanding of the universe. Like this is a perfect example. I mean, we've known since whatever age that, you know, most of the things we touch and feel and interact with are made of matter. We know that matter is made up of atoms, which is made up of electrons and nuclei. We've even gone further than that. We've found that there are these protons and neutrons that make up the nuclei. And we've even gone deeper in. We know that the fundamental particle in this situation is, here's the quarks. So each of these, the 3 quarks make up the protons, they make up the atoms, they make up matter that we interact with. And this is fantastic. I mean, this is great. Thousands of years of human understanding captured right here in this slide, and this is what we've known since we were in whatever grade in school you learn about subatomic particles, right? And I mean, we hear stories like this all the time, and we hear all the things we've figured out, but really, normal matter only makes up 4% of the matter in the universe, of the energy content of the universe. So if I want to make a new universe, it would contain 4% of that whole thing I just described. So the rest of the universe is made up of dark matter, 21% we think, and then dark energy, 74%. And so that's kind of depressing. No, but it's not really depressing. It's more, there's a lot out there we don't understand. We don't spend a lot of time with popular science talking about how we're like, that doesn't really fit in with anything we know about. We want to sound good when we write these popular science articles. But really, I mean, this is the situation that we're dealing with. We don't know what this is. We don't know what this is. We're doing pretty good here. We feel good about this. So, and I'll just say for those of you that have ever wondered, here we have the word energy, and then here we have matter. Why are matter and energy all in a pie chart together? If you all know the famous Einstein's equation, E equals mc squared. The energy equals the mass times the speed of light squared. You can convert mass into energy. That's how nuclear bombs work, or other less horrible things. But energy and mass are at some level equivalent. So we can say, if we use that equation, energy equals mass times the speed of light squared, we can say there's this amount of dark energy, and I can multiply the amount of dark matter by c squared, and I can multiply the number of normal matter by c squared. And that way I can see how much energy would be in each component. So that's, maybe you've wondered to yourself why we say 74% dark energy. That's what that means. That means if I converted everything into energy all at once, 74% of the matter, that's how much energy there would be in matter. So this talk is about trying to understand 21% of the universe, dark matter. Yeah.
You were missing 1%. What do you think that is?
Oh, probably a rounding error. Maybe, well, no, there's also photons, but those are less than 1%. I'm going to go with a rounding error. Yeah, that is funny. I didn't try and add that up. I blame the internet. Everything's fake there. Okay. So there are other, photons are not being included here, but again, that's less than a 1%, so I do think it's just a rounding error. Okay, so why do we think dark matter exists? Okay, because of gravity. So gravity pulls things toward each other, and this is a highly scientific demonstration of this in practice. The moon orbiting the Earth because of gravity's pull. One thing that's important, if you have a stronger pull of gravity, you have a higher orbital speed. So we can go out, we can look at how fast things are orbiting, we can measure how much gravity there is, and then learn about how much mass there is. So this works around in our solar system. So here's our sun, the planets go around the sun. The things that are closer to the sun feel a stronger force of gravity because the force drops off as you get further and further away. So these planets orbit really quickly because they have the strongest pull of gravity. Then further out, you have these guys going a lot more slowly because they're a lot further away. The force of gravity is weaker. It all makes sense. What? Okay. That is strange. That got flipped. Okay. So what happens if we look at a galaxy? So galaxies have these beautiful spiral arms here. The stars that are further away from the main body of stars, based on what I was just explaining, you would expect these stars to be orbiting more slowly because they're further away from where most of the stars are, right? These should go slow and these should go fast because they're where the main body of stars are. So if we wish as a video, this is what we would expect without dark matter. So notice these stars are orbiting a lot more slowly than these ones. With dark matter, and this is what we actually see when we look at galaxies, okay, they don't actually spin in real time, but if we look at their velocities, these stars are actually these stars are actually orbiting as fast or even faster than the ones in the center. So they're experiencing as much gravitational pull as these ones, even though they're further away from most of the stars. And we can look at that on a plot here. So this is a disk galaxy. This is the velocity on the y-axis of the stars. People are measuring the velocity of the stars as a function of their distance from the center of the galaxy. So near the center of the galaxy, we would expect that as you get farther and further away, there's less pull. What we see is what we saw there. The velocities are getting higher and higher as you get further from the thing that you can see that should be causing the pull. That's the opposite of what we saw with the solar system. With the solar system, the planets that were further away from the sun were going slower. Here, the stars and gas that are further away from the main galaxy are going faster. So the explanation that we think makes the most sense right now is that there's a bunch of extra mass that we can't see, but that's creating an extra gravitational pull out here and creating this effect. It's pulling on these stars even more than the stars in here are, and they're orbiting faster. So we can look at this picture one more time. So here you have, the idea is there's a lot of dark matter, so that these guys are orbiting a bunch of dark matter that's creating that pull that's allowing that to spin faster. So this is one of the fundamental ways we first observed the existence of dark matter. And it's not just in the spiral rotation curve of galaxies that we see the effect of dark matter. We also see it when we look at how galaxies orbit around each other. So our planet orbits around a star. Our galaxy has billions of stars in it. But then there's also billions and billions and billions of galaxies. And they orbit around each other because they feel gravity. Those groups of stars feel gravity from other galaxies. And we can look at how fast they're going around each other. And their speeds are higher than we can explain from just the starlight that we can see. There has to be some extra matter creating some pull that allows them to orbit quickly. And finally, we have the cosmic microwave background. So these are photons. These are light that gets emitted very early in the history of the universe and has traveled through space to get to us today. And by looking at how these clumpy patches, by studying how clustered they are, we can learn something about how clustered the universe was when those photons were emitted. A clustered region of the photons is correlated with a clustered region in space when the photons were emitted. We can make a plot like this one, which I'm not fully going to explain, but it sort of shows regions where the light photons are clustered. So this blue line is the clustering signal we expect if there's no dark matter. And the black dotted lines are the observation, which can be fit arbitrarily well if we assume there is dark matter. So the clustering of light in the early universe, the rotation of galaxies around each other, the rotations of stars in galaxies are all giving us a smoking gun signal for some extra matter that we can't explain except by having an additional particle. Now, I'm going to talk about the dark matter theory today. It is so far the only theory that can explain all of these observations I've described, and it is, by any standard, a wildly successful theory. This is the entire history and evolution of the universe from very early times to present that is being matched by invoking this extra particle. People do actively research other explanations for the phenomena I've described, though, and that's very important because we haven't detected dark matter particles yet. Okay, so we're going to talk about the dark matter theory. So this is the dark matter theory. All of those observations I just described can be explained if there's some extra matter that we can't see. It has to be a new kind of particle. It cannot be a normal particle known in the so-called standard model of physics. It cannot interact with ordinary matter except via gravity. It could interact a little bit with ordinary matter, but not very much. You can quantify those statements and make them more scientific. It can't interact with itself very much either. It definitely cannot interact with light. That's important. That cosmic microwave background picture I showed you would not work if dark matter interacted with light at all. And it makes up about 85% of matter. Okay, this is another different number from. So this is 85% of matter. And this is the cartoon picture we have of dark matter. We have our galaxy, which we've probably seen a lot, like spiral arms orbiting around, and then we have a much more extended puffy cloud of particles, dark matter particles, that the galaxy is sitting inside of. So in this theory, this room would be full of dark matter particles. They're just everywhere, they're puffy, they don't interact with anything. Yeah?
So if it doesn't interact with matter or dark matter without gravity, doesn't it interact with light via gravity too?
Yes, that's exactly what we're going to come to later in the talk. My research depends on that, so it's a great question. It interacts, via gravity with light, yes. Okay, okay. And then we have a lot of different candidates for dark matter. What could dark matter be? So we don't love inventing a new particle to explain things. That doesn't make us feel good as physicists. We want the universe to be simpler and not more complicated. But if we have to invent a particle, it would be great if it fixed one of the many other problems we have in physics that we can't explain right now. And we have a bunch of different classes of particles or even primordial black holes, which would each help solve some other standard model problem. So the standard model of physics are basically the whole set of what we know about the universe. So each one of these candidate particles would solve some other standard model problem, which I haven't gone into today. So just to list them out, we have weakly interacting massive particles, stereo neutrinos, axions, primordial black holes. On the right is the computer simulation of axion dark matter. So here, this zoom-in section, this would be about the size of our Milky Way galaxy. And you can see that the dark matter here is kind of this puffy extended structure I was describing. And then we would also get these crazy filaments and these weird interference patterns. That's a feature of this axion dark matter. So how are we going to learn? We have all these candidates for dark matter. How are we going to learn about what dark matter is? Well, let's take a look at a computer simulation of one kind of dark matter. I just showed you axions. Now I'm showing you a much more standard dark matter model that we use kind of as a default because it fits a lot of the observations well, and it's very simple to simulate compared to some of the others. So this is cold dark matter simulation. This is if we could see dark matter, if we could put on dark matter goggles and dark matter, what's cold dark matter, or weakly interacting massive particle. The universe will be made up this filamentary structure, this kind of cosmic web, we call it. And where the filaments meet up, you get large, dense regions, and then you get these big, puffy clouds of dark matter. So this is what the cartoon picture I was trying to draw here. This is what it really would look like from a computer simulation if this was dark matter. So you see we have the puffy structure, and then a lot of smaller structures that are gravitationally bound to the bigger structure. So it's not just one halo around our galaxy, it's many, 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 each with their own structure, possibly with their own galaxy in it. And this is how we can get a handle on some of the models of dark matter. So different particle models of dark matter predict different things about what structure looks like at present day. So here's a simulation again with the weakly interacting massive particle. This is the same thing I showed before, but a different simulation. And then on the right, I have a different dark matter candidate. I have something called a stereo neutrino. This dark matter candidate would potentially explain why neutrinos have mass. So that's an example of a standard model problem that would be solved. We don't know why neutrinos have mass. Anyway, so if you compare the two simulations, you see that the filamentary structure and the number of large dark matter halos, because again, these are dark matter simulations, those are the same. The large scale structure is the same. They have to be the same because that's something we can measure pretty well by looking at galaxies and seeing how they're distributed. We have a pretty good idea what the large scale structure of dark matter would have to be. But on small scales, on the really clumpiest scales, you can see that the picture on the right has a lot less structure than the picture on the left. And just for scale here, this bar is 100 times the size of the Milky Way. So this little thing, the Milky Way, would be a little blip right in there, just so you get a sense of scale here. So by changing the particle nature of dark matter from one theoretical model to another, I change the number of structures I predict to observe in the universe. And some dark matter models, including this default dark matter model that most people use in their simulations, predict that there could be more dark matter structures in galaxies we observe. So you have just the cloud of dark matter particles, but no galaxy sitting in the middle. So just to show you what that would look like, on the left we have a simulation of the Milky Way halo, again, the Milky Way cloud of particles, and also what we call these subhalos, which are gravitationally bound. They're orbiting within the gravitational influence of the Milky Way halo. And then on the right, we have the Milky Way galaxy and the galaxies we see around the Milky Way. So if we remember our picture, galaxies, we think, live in their own dark matter halos. That's how we explain the rotation curve of the stars. So each of these could be mapped onto one of these. So if you were just to say to yourself, I'm going to count the amount of structure by looking at the number of galaxies and comparing to this picture, I would say, no way, that's out. But there's a lot of things we know that can suppress star formation if there are these low mass halos. Lots of things that would make it easy to just eject gas before stars could form. So really, this is still a viable theory, even though when we look at the sky and we count the number of galaxies orbiting the Milky Way, it's much lower than the dark matter structures predicted by this theory. One cool thing is, so these galaxies, they are called satellite galaxies, just like the moon is a satellite of Earth. You have satellites of the Milky Way, but they're entire galaxies. And the large and small Magellanic Clouds you can see from the southern hemisphere. So next time you're down there, check them out. I don't think I've been to the southern hemisphere since I learned about them, and so I'm still waiting for my chance to see them. Anyway, what else did I want to say about this? Yeah, so one of the questions we want to ask is we want to be able to count these dark matter halos. We want to test these different particle theories of dark matter, but without relying on galaxies to count them. That way we could potentially see if there are just completely dark halos out there or not, and rule out these different particle models of dark matter. Okay, so these are our science goals, just to summarize. We want to measure how many of these little clouds there are, and these little halos. And we want to see if there are completely dark halos. That would be cool, but also it would completely rule out certain classes of dark matter models, and it would prove the existence of these particle gravitating clumps. Okay, so this is where we're getting to the gravitational lensing, using the James Webb Space Telescope images to test different dark matter models, and these are some different gravitational lenses. Okay, so this is where we come to your question. Gravity pulls on light, so gravity pulls on matter, keeps us stuck to the Earth. It also pulls on light. So here's a nice computer simulation, obviously, of the sun. You have light from a distant star. It should, if it was normally following a normal path, it would just come to us this way, but it gets bent around the sun, so we think it's coming from here. So that's gravitational lensing. This was a fundamental part of Einstein's theory of general relativity, that this would happen and the amount that it would happen. So Newtonian physics actually does also predict some kind of gravitational lensing, but it's different. It's a different amount. So anyway, fun fact for the aficionados in the audience. The observation, the way they were able to prove this general theory of general relativity. So you need, back in 1919, you need something really massive, sun, check. But then you need to look for these stars getting deflected near the sun. So how do you see stars near the sun during the day? Sounds difficult, sounds bad. They used a solar eclipse. That was a perfect time to do this, because then they could see stars near the sun, and then they could measure their relative positions compared to when the sun isn't there, like at night. You can just go back to this spot and be like, what are you like normally? And they could see that this star, for instance, was significantly deflected when the sun was nearby it compared to where it's normally observed. We could observe gravitational lensing. This was the confirmation of Einstein's theory of general relativity. This is a New York Times headline, which I just absolutely love. Lights all askew in the heavens, men of science more or less agog over results of eclipse observations. Einstein theory triumphs, stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. This is some reference that I do not understand. If somebody could explain that to me, I would love it. Is there like a biblical thing there? Honestly, I don't know. But they have like 18 different headlines. They're so excited in their committee meeting. But you can see, this is an amazing thing to observe, right? Like it's actually stars moving in the sky. So this is important. The fact that gravity bends light is essential for GPS to work. So GPS works not with visible light, but with other kinds of light that we can't see. I forget if it's microwave or what it is. Anybody? Anyway, I think it's microwave frequencies, but it is a kind of light that's just not visible. And when the beam of information goes from the satellite to Earth, it gets distorted and bent, just like the starlight is happening. And if we didn't take that fact into account, our GPS calculations would be off. So this stuff kind of all seems sort of fun and cool, but it really does affect our everyday life. Okay, so we're moving on with the gravitational lensing, though. So if everything's aligned just right, you get not just a little deflection, but you get multiple images of the background source. So you'll actually see like multiple copies of that background source. This is a simulation of Earth and the sun doing a lensing of a background galaxy, and you see this distorted image here. And you can achieve the same effect with a stem of a wine glass. So here you have a kind of a point source, like a candle, and if you hold the wine glass at different angles, you can get 3 images, 2 images, or even a ring like this. So obviously, in this case, the path of the light is being bent by glass, and in this case, the path of the light is being bent by gravity, but geometrically, you get the same solutions to your equations, even though the thing causing the lensing is completely different. So how do I use the fact that you can get multiple images? So the image positions and brightnesses are sensitive to small structures. So let's say this is a gravitational lens that I'm looking at from this side. I have my telescope here by Earth, and I have a background hexagon. Wait, how many sides? 1, 2, 3, 4, 5. Hexagon. I have a background hexagon that's shining light, and it's being multiply imaged by a galaxy and its dark matter halo. If I put a little perturbation along the line of sight, it will distort one of those lensed images. And I can learn about the mass distribution of these perturbations by looking at how distorted my lensed images are. So here, for reference, is a face-on view of a real gravitational lens. So in real life, I look at the different brightnesses of these images. I compare that to what I would have expected with a smooth mass distribution, and I can statistically learn how clumpy the universe is. If I learn how clumpy the universe is, I can rule out different classes of dark matter models. And this is a simulation which is a little bit more realistic of all of the many, many structures we expect to see along a typical sight line for the gravitational lens like the one I showed you. Okay, so here's a real observation, just to show you what this looks like. So this is our data, right? We don't have a side view, sadly. We have a face-on view of the gravitational lens, a chicken that loves astronomy. I know, it is a beautiful lens. Thank you. So this is a real observation. So you see 4 images here, and the thing in the middle is the galaxy that's causing the deflections to occur. So on the right is the best fit model we can get to the image positions and brightnesses if we just assume there's no clumpy structure. No clumpy structure at all. We can fit the image positions really well, but we can't match the fact that this image is being really demagnified here compared to this one. So this is an observation of some clumpy structure along the line of sight causing this image to be demagnified. That's our observation of clumpy structure in the universe. So that's our signal. And the point is that we look at a lot of lenses. You can't just look at one. You have to look at a lot of lenses and count how many times you see something that looks like a clumpy structure, and you see, is the universe more clumpy or less clumpy? And then you can learn something about what kind of particle physics you have. And with 8 lenses, we were able to rule out the scenario on the right. So we could rule out models which predicted a really smooth mass distribution. So this was my research. And this is I don't know, just so you know, I know what I'm talking about. This is all the parameters of the dark matter we inferred for this paper. But the main thing is this picture here. We ruled out that the universe was this smooth. It looked more like this picture. But we weren't able yet with these 8 lenses to confirm that there were dark halos. So how do we make progress? Okay, so this is where the James Webb Space Telescope comes in. So the James Webb Space Telescope lets us do lensing, but with an even finer light beam than what we were able to do before. So why does having a finer light beam let you measure clumpy structure better? We can see that with the cats. So on the left, on the left and right, we have the same size cat. It's one of those weird optical illusions. It looks bigger here. Anyway, but you can see, like, if you were to shine a smaller light on this cat, on the cat on the left, it's blocking, let's say, I don't know, like 75% of the light on the left. I have the same size cat in front of a much bigger light source, and it blocks a much smaller fraction of the light. It's much harder to see that there's a cat there because it can't block as much of the light. So if I have a finer beam, I can detect a smaller dark matter halo because the dark matter halo doesn't have to magnify as much of that light beam, right? Remembering, the dark matter is not actually blocking the light, so that's where this analogy fails. The dark matter doesn't block the light, it just magnifies and distorts it. So, but it's the same kind of general image we can have in our head that if I have a finer beam, it doesn't take as much dark matter to bump it. And so if I can measure lower mass dark matter, I can get an even better handle on which dark matter model is correct. And this is slightly more scientific depiction of the cats. We have a change in the magnification on the y-axis, and then a position, the distance between the dark matter halo and the center of a lensed image, and this is a simulation we did. So the red line is how magnified a James Webb Space Telescope, or how magnified our previous data would have been by a dark matter halo with a given mass. And so that's this line here. It would have been magnified by about 2% compared to the smooth model prediction. But with the James Webb Space Telescope, we have this finer beam here, and it's exactly like I was just saying. The same size dark matter halo has a much bigger effect on that light beam because the light beam is finer and it's just easier to block the light or magnify it or distort it. Exactly this effect here. So in this case, the James Webb Space Telescope is 6 times more sensitive to this mass scale. So that's why we want to use the James Webb Space Telescope. So, okay, so this is the part I think where I included some slides from the children's talk because I thought it would be fun. Here, wait, no, we're not there yet. This is for adults, so you can be serious still. Okay, so to do our experiment, the laser beam we need to look at, why do we need James Webb to see the finer laser beam? Because it's in the infrared. Okay, so almost everything emits light, normal matter, not dark matter, which is really almost everything, but I'm, biased by being a human made of matter. So we know we can see in the visible with our eyes, but obviously, just like I was just talking about, there's all these other wavelengths of light, like the wavelengths of light we use for the radio, for X-rays, right? And we know like cats emit light. So this cat, it's read to be 87 degrees, but I think that that's just because of the fur. I don't think it's dead. But anyway, the cat emits light in the infrared. Like we can't see a cat emitting light with our eyes, but if you have a detector in the infrared detector can see that light. The Earth's atmosphere emits light at, I'm going to just say 2 microns, which probably doesn't mean much, but that's sort of here on this color bar. The thing I need to measure to get that fine light beam emits light at 25 microns. And the Earth's atmosphere is really bright. So here's a very beautiful quote from one of my very annoyed colleagues. Trying to observe in the infrared from the ground is like trying to see stars while your telescope is on fire and the sky is on fire. So the atmosphere, because it's emitting photons like everything else, and there's a lot of it, is so bright in the infrared. You cannot measure these wavelengths that we need to measure from the ground. You just can't. You have to send your telescope to outer space. So I think, yeah. And not only do you have to send it to space, you have to cool it in space, right? It's not cold enough on its own. You need to keep that thing cool because otherwise the observatory itself will be emitting so many photons you can't see the photons you want to see. Okay, this is the part for kids. Okay, how many giraffes high do you think outer space is? Let's get some order of magnitude estimates from the audience. I was going for audience participation with the kids. What? We have million? Okay, all right, do we have? Obviously, do you know how many kilometers a giraffe is? I like this. This is like way higher level of thinking than I was expecting for this. I was really expecting cute answers from kids, like 10, like the biggest number they could think of, 100. You guys are boring, but it's a million is a good guess. It's actually just 100,000. So you guys are, by astronomy standards, that's basically the same as 100,000. I'm serious. Okay, that was just for fun for the kids. But now you learned something useful you can tell people. Here's the launch of the James Webb Space Telescope. I don't know. It was really cool. I slept through it. My alarm didn't go off. But also, I was so afraid. I was so afraid something would happen. I woke up like, I don't know, an hour after it launched, and I was just so glad to see that it was okay. And then, so these are some cool things. So the telescope, the rocket had to open up to let the telescope out. And then the telescope is actually wider when it's open than the rocket is. So they had a whole series of deployment steps. This is a sun shield to block the light from the sun. And then you can see it stands up. And then these little mirrors also deploy outward. There was like, I don't know, 100 steps that had to absolutely work or nothing, or the whole observer mission would have been dead. It's terrible. You could watch so many cool videos about it. But this is why it's so scientifically important, the thing about the atmosphere. So we've had instruments in space before that can measure the wavelengths I'm talking about. So WISE is one of them. We had Spitzer after that. The other really important thing that makes my science possible is the mirror size. If you have a bigger mirror, you have better resolution. You have a sharper image. So this is the evolution of the WISE data. Spitzer, this is an improvement, but this is something else. Like, this is paradigm changing, the resolution we have now. So this is a real image with the James Webb Space Telescope now that it's out there. And then I think the other thing I wanted to say, just because it's another cool fact, is the moon goes around the sun, or goes around the Earth. Sorry, the next thing I was going to say is the Earth goes around the sun. It's good. Little check for the audience there. So Webb follows the Earth around the sun like that. So it doesn't go around the Earth, it goes around the sun. So it's much further away than the moon. It's at a stable point gravitationally called L2, and it orbits with the Earth around the sun together. And the Earth is always between James Webb and the sun, and we have this fancy shield thing, which is many layers of this reflective material just to keep those evil photons away from us. Okay, so this is it, you guys. So this is my data that I got last night. This was the data I had before from WISE, that telescope I was showing you. This is it. So this is my experiment. It's my group's data. What was I going to say? Oh yeah. So far, I've let's say less than 100 people have seen this image. So my collaborators and the 20 so people who were at the talk this morning. So you're seeing this data. No other scientists can see this. This is private data. I don't think you guys can do much with it because this is a really crappy screenshot, but anyway. So we have the 4 gravitationally lensed images. That light is coming from that source, like I was saying. It's going to make us really sensitive to dark matter. So this is our first data we got from this. We are expecting 30 more lenses to be measured over the next year or so. And yeah, we're super excited. So this
one object lensed out 4 times?
Yeah. Mm-hmm. Yeah. It's clumpy? Oh.
You said the 2 models, one was smoother and one was...
Oh, yeah, no, we can't. You're going to publish a paper on that. So, fun fact, somebody like that, CMB, you remember the big watermelon, blue and orange thing I showed, the cosmic microwave background? So, some of that data got presented in a talk, and people took a photo of it and used it, not public, but like a science presentation, at a conference, and people took a photo of it and tried to use it to get ahead on their data, because that data hadn't become public, And this led to like a massive mistake because the data quality wasn't good enough. So don't try and take a camera shot with your phone. You'll be embarrassed. Anyway, that's a real story though. That happened, and that led to a major, like, people were like, we discovered this amazing thing, and then it wasn't true because the data set wasn't good enough, because you can't go based on a screenshot of a PowerPoint presentation. Anyway, so okay, this is another simulated image. So we really do think with this data sample, we will detect the completely dark halos if they exist. So we've done simulations, if we get the data accuracy we need, and based on our initial data sample, it looks good. We think we'll be able to see completely dark halos if they exist. So we're very excited. And we'll be able to tell if the picture on the left is correct and there are a lot of small dark structures around the Milky Way, or if all we see is what we get, there aren't any dark halos. And so we should be getting results at least as good as what we had before by early in the summer. So we should have about 8 lenses again, and we'll do a comparison paper. And then I think by next fall, we should hopefully have like this result, whether or not we see these. So stay tuned. And that's all I have to say. Ask questions.
Yeah. I have a question. I'm just curious to know if, we do have a planet like Earth, kind of similar to Earth in this galaxy or in our galaxy out there in space. I don't know, since you're a scientist, I'm just curious if we do have something similar to Earth.
So we haven't found anything quite like Earth yet. We're not there yet. There are so many stars. Here, we'll go back to the galaxy cluster. Oh, the giraffe, wow, okay, this is ambitious. I want to go to this one. Nope. Here. So this is like a tiny, tiny little snippet of the universe, right? And each one of these is a galaxy. Each of them has billions of stars. So certainly in the whole universe, I think it would be unreasonable to think there isn't something like the Earth. I guess I would think certainly in our own galaxy. I don't think we know yet how many there are, though, or how likely we are to find one. I guess that would be the answer. So I guess if I was betting, yeah, it's out there. I don't know if we'll... That would be we definitely don't know yet. Yeah, and we don't even know, actually, we don't even have a good idea of like how probable they are. We're still kind of at a point where Earth-like planets are difficult to find. Yeah. So if we could say, oh, it's 1 in a million, I could give you a number, but we're not even there yet. Yeah. Yeah.
First off, congratulations on that image.
Thank you.
I know that's a long time coming.
Yes.
So when you were showing the images of what the different candidate particles would predict for the structure of the universe,
Yeah.
They're just a few slides away there.
Yeah.
They all look like foam.
Yes.
Is that just me, or is that something that you guys talk about? Like, oh, it looks like the universe is kind of foamy.
Yes. So the structure is it's distinctive. It's definitely not homogeneous, right? There's definitely, like, if you point one way or another, you'll see something different on this scale. So what happens, and we observe this too. So this is why both simulations create this, because it's something we can see when we look at galaxies. So what happens is gravity pulls things together, but at the same time, the universe is expanding apart. And those combinations give you these kind of, in 3D, they look exactly like a foam or bubbles or sheets. Yeah, exactly. Yeah, it's exactly the same idea. So in this case, space is expanding, and then you have like a double whammy. This region then has less matter in it, so it expands even faster than this region. Yeah, so people study these voids and try and see, learn about how galaxies form in the voids, all kinds of things. So definitely it's a great observation that it's the same process as a soap bubble. Mm-hmm. Yeah.
So why dark matter? Was there something that
It sounded cool. I think, so I liked physics in school. I don't know, I wasn't like, oh, when I was a kid I wanted to do this, right? That wasn't me. I liked physics, and then I think I really like astrophysics because you get to do this fundamental physics stuff that it can be hard to do. Like, how are you going to do, you can't do this experiment on Earth, right? We can't, we don't even, if we couldn't see outer space, we wouldn't be thinking about dark matter at all or dark energy at all, right? We'd be happy with our 4% of matter. So I think because of that, I'm very drawn to that side of astrophysics where you're looking at physics that's occurring that you wouldn't be able to observe on Earth. But I mean, honestly, it sounded cool is about like the same thing. I was like, that is very interesting and strange.
So were you studying physics at the undergrad?
Yeah, so I liked physics in high school. I was like very nervous. I was like, maybe I'm not good enough to do physics in college. And then I just tried it, and I just really liked it better. I started as a bio major because I thought, oh, I can't do physics. I'm not good enough, or what? Just, but I found that I knew the Krebs cycle was important. Like, my life depends on it. And I just didn't care, I'm sorry. It's very, I know. No, that's the thing. Because people have said to me, I've had parents say, why didn't you be a medical doctor? If you can do this, why wouldn't you have been a medical? But it's this is what I love. And so, yeah. No, but it's amazing that we know the Krebs cycle. I don't know how they do it, but yeah. Anyway, I just liked it.
Thank you.
Yeah.
Just in my mind, do you think galaxies are continuously forming as we speak out into this infinity of space, or is there a set number of galaxies where you as a scientist think we can't go past that? That's the red line.
I think, yeah, so what's interesting, I'm not totally sure what the answer to that question is. Because galaxies form when they get gas collapse, gravitationally falls in, and then they cool and form stars. And I don't actually know if we expect new gas to be forming new galaxies at a significant rate at present day. So that I'm sure someone knows the answer to that, but I don't know. Yeah, I think in general, probably there aren't a bunch of new galaxies just popping up, though. So in general, we think most of the dark matter structure is kind of there.
Stars are forming and dying, but galaxies are not the same.
Yeah, I don't know how many. I almost want your email so I can just go ask somebody who would know the answer to that. That's a really good question. Yeah, thanks. Yeah.
Okay, so you mentioned how astrophysicists want to count dark matter halos.
Yeah.
So I was wondering, is it possible to use citizen science or using the public to help count and gather that data?
Yeah, so the thing with the dark matter halos, so people use citizen science and astrophysics all the time because we have a huge data set, the universe. So people do things like classify galaxies for us, and that's Galaxy Zoo, and that's been really successful. And the other citizen science project I know about is, I think it's something warps, space warps. Anyway, we want to always find more of these gravitational lenses, so we have people just look through images, try to find more gravitational lenses. We have computers that can do pretty well, but humans are the best pattern identification system so far. We can't have the humans look at the dark matter halos yet because we can't see the dark matter, but we can have them do things like find the data we can use to do the dark matter. So space warps, I'm pretty sure that's what it's called. So if you want to check it out, I've done it, it's pretty fun. And they put in fake lenses for you, so it's not just you saying no a million times, Yeah.
As a result of the telescope, have there been recalculations of the speed of the expansion of the galaxy because there's so much more visible matter that's
Yeah.
being seen?
Not yet. So we really are in the early days. So what I've seen from interesting new results are things that'll be a big precision measurement, and I'm sure it'll happen within the next year or so. So the interesting things I've seen, which we're seeing more bright galaxies early in the universe than we were expecting to see. So that is one of the interesting things. So the things we're seeing that people are confident on reporting are things like bright things or like, very, very coarse scale kind of things. People aren't comfortable yet making these precision measurements. So more bright galaxies than we were expecting, which means galaxies formed more stars earlier than we were expecting. Which is, if it's true, it's early days. If it's true, it would really put some tension in some of our theories for the evolution of the universe. The other thing I saw that was really interesting is just that the way we can look at how different elements are distributed in galaxies, and they were seeing some galaxies that look like they have a very different element distribution from what we were expecting, which indicates the way that the gas is moving around in them at these times was really different. So I think we're going to see a lot of stuff like that, where it's like people have been saying for years, no, this is how it works, and then you just take one look and you're like, well, no, that's not true. So that's what that image I showed with I'll zoom forward again. I mean, you can just tell by looking at, sorry everyone.
It's okay.
Okay, thank you. Okay, here. I mean, you could just tell, right? This is paradigm changing. You're going to just see stuff. It's like, okay, well, we were wrong about that too. Yeah.
When you write the computer models, you're going to run your data through.
Yeah.
So you have fundamental mathematical models that you compose whatever you're going to run your data through, and then it's going to look for standard models that fit. Does that make sense?
Yeah. So that's like, I'll just kind of repeat what you said, but basically what it does is what we do actually is take specific models. So we can't really look through all the models. We have to say, I'm going to compare like cold and warm. I'm going to compare a lot of clumpy and not as clumpy, and I'm going to see which one I get. So that's the sort of models we run. We don't start from like square one.
No, but there's a mathematical model that you compose.
Yeah, so what happens is someone runs a really high resolution computer simulation, and then we do an approximation to that and put it in our simulation to do the gravitational lensing. Yeah.
And the more data helps support this definitely.
Exactly, yeah. So working out the statistics for this was actually very important. That was something my group did. And then working out the statistics, and then the ability to do that lensing calculation, the simulation of the subhalos and the lensing calculation quickly enough to do a robust statistical comparison was super important for this. Yeah.
So statistically it's pointing towards this other model.
The clumpy one, yeah. But so what I'm excited about is going like way further into the, yeah. Yes. Yeah.
How much James Webb time did it take to get your image?
So I think the image I just showed took a minute. So James Webb is amazing. It's a tennis, the sun shield is like a tennis court, it's fantastic. And then to point to a new thing, it takes like a half hour because it has to stabilize itself and be really careful. And then I just look at it for a minute. But it was really designed to stare at the same object. I think I heard something like it could stay fixed observing something for a week. My case is really on an extreme end where my targets are really bright and I really need it because of the spatial resolution. The longest exposures I'm doing are about 10 minutes. So I have 3 1-minute exposures and a 10-minute exposure.
But like you said, one of the benefits of the James Webb, other than its resolution, is that because it can stay focused on a fixed place in the universe for much longer time,
Yes.
before you can see much fainter.
Yes. So I'm not taking advantage of that ability at all. I'm like, I don't know, choose your aphorism for someone who's wasting the abilities of something. But yeah. Yeah. How much time does everyone have? So you have to apply. So most people don't have any. So you have to write a proposal. I wrote a proposal 2 years ago in the fall. And we had to say exactly what we wanted to look at, for how long, what we were hoping to find. We had to convince a group of astronomers, the time allocation committee, to give us time. I don't remember exact numbers, but there was about a 1 in 10 chance of getting time on the telescope. So we were able to convince the time allocation committee that this was a good program. My program has about 40 hours. It's called a medium proposal. Like I said, most of that time is being charged to us because we're pointing at a lot of different targets. But anyway, it's 40 hours. Yeah.
That can't be cheap, but how does the funding come?
So NASA, so the government, taxpayers, thank you, they pay for the telescope, and yeah, they just pay for its operations throughout the year. So not only...
Oh, so the funding to use it basically is built into the...
Yeah, so but they actually, if you get your grant, if you get your time awarded, the government also gives you money to make sure you can do a good job analyzing the data. So I'm getting money from NASA to pay for researchers to be dedicated to analyzing this data. Yeah, which is really important because analyzing that data, it looks really simple. You know, we're going to want to be really, really careful about exactly how the telescope is distributing the light out and make sure we do a really good job there. Yeah.
Are we able to see things that our naked eye can't see through the telescope?
Oh yeah, like none of the things I've shown you could you see with your naked eye. None of them.
Are we able to dark energy and matter also?
So we're hoping we can see the effect of dark matter through the gravitational lensing, and then we can see the effect of dark energy through the expansion of the universe. So yeah, we can see the effects of both with the telescope.
Also, we can't see them directly.
No. Yeah.
Interesting.
Yeah. Yeah.
When you're handling the telescope or pointing the telescope, are you doing this like from your lab?
No. Fun stories. You give them a list of coordinates, and they give you the data. And on Sunday night, they hadn't told me my target was going to be observed this week, but I was like, you know, I'm just going to just double check my coordinates one more time. And I saw that the coordinate was off for the first target we were supposed to observe, which they do not reobserve if you make a coordinate mistake. So I had to email them. They had to like re-upload the correct coordinates. It was a nightmare. Oh my God. It was a nightmare. Thank God we got it observed. But yeah, we send them the coordinates. We tell them how long, all the things, and then they just upload the data to a server. Yeah.
So with the bulk dark matter model, how does it interact with like really dense objects like a black hole? Would it be able to escape? Would it like be able to interfere with other mass or with light through gravity to make it so that something else could escape the bulk of the mass? Or
I think so. In principle, the dark matter should get sucked into the black hole, just like other matter does. So the gravitation, just like the black hole can pull in light and everything, we expect it should pull in the dark matter as well.
So as long as the interaction is through gravity, we expect it to behave basically the same as normal?
Yeah, that's right. Mm-hmm. Yeah.
With the coordinates you were just talking about, is that an XYZ type of setup, or is it latitude, longitude?
It's latitude, longitude on the sky. So it's called right ascension and declination. Yeah. Yeah, I just had one number off. Would have missed the whole detector. Oh my God. Yeah. Oh.
You had a slide with the Milky Way in the center of it.
Oh yeah.
And you have other galaxies
Yeah.
around it. Is the Milky Way so massive that it has galaxies being influenced by it?
It is, but mostly it's the dark matter halo. So most of what these little galaxies feel would be the dark matter halo. Oh, so this dark matter halo, if I were to remove the Milky Way, the dark matter halo outweighs it by a factor of 10. So.
But is the Milky Way one of the larger galaxies, and it can
in this area?
create that level of influence?
Well, like I said, I could just delete the Milky Way from this, and I would see the same picture almost. So the main thing we're seeing that's influencing this is the dark matter halo of the Milky Way.
Oh, okay.
Yeah. Obviously, that's not completely true. It's only, it's like 1% of the mass. But, it is obviously having some gravitational effect. But the main thing, if I wanted to approximate this system, would just be the dark matter halo.
So really, the Milky Way is not the center of the...
No, it's sitting in the middle of the dark matter halo. Yeah. So it's sitting in the middle of the dark matter halo. The Milky Way sits in the middle of the dark matter halo, but it's not the center. I mean, it's not what's creating it. Yeah, yes. Yeah. Yeah, yeah.
So somehow we have matter that makes stars in the middle that can come together and do fusion and everything, but the dark matter doesn't.
Yeah, so this is super important. So normal matter.
That's the difference.
Yeah, exactly. Yeah. So that's why I said one of the key things is dark matter can't interact with itself significantly. So normal matter has charge usually, and when you accelerate a charge, you emit photons. So accelerating charges emit photons. This is how light bulbs work with filaments. And so that's a way of losing energy. So just like our planets going around the sun, they're never going to fall into the sun. They conserve their angular momentum. But if they were charged, they would be radiating energy constantly and sinking into the sun. So charged particles can sink inward because they're radiating energy electromagnetically. And they can also lose energy because they just collide with each other. And that creates the clumpy structure. That's what allows galaxies to form. Dark matter doesn't have any way to lose that angular momentum, just like the planets don't have a way to lose that angular momentum. The planets will orbit forever. So dark matter is just like that, and it stays in this puffy cloud. So that places an important limit on how much dark matter can interact to match our observations. Does that answer your question?
Yeah, it does. Well, to some extent. Is it just that you can't get close enough together to do that? Or this is another question I had about this, and I don't know if it's in your realm, but you must have thought of it to some extent. But what do the string theory people think of this?
I don't know what they think.
Because it seems like it's taken all the forces and say, no, wait, some of those don't exist in this matter. This matter only has gravity.
Well, we know some particles only interact with a subset of forces. Neutrinos do not interact with a strong force, for example. So there are particles that just have chosen to only interact with a subset of the forces. And why not dark matter? Yeah. Yeah.
The primary evidence of dark matter is that it doesn't, the observations we make don't fit with what we thought was going to happen.
Yes.
Why are we focusing, or the consensus is focusing on dark matter as opposed to reformulating our theory?
Well, that is the reformulation.
That's reformulation.
Yeah. So I think whenever you're doing an experiment and you see something you don't expect, the first thing you think is, I messed up my experiment. And so people spent a lot of time doing this measurement over and over. They're like, it really doesn't work if we don't have dark matter. So that's where they brought in this idea. Yeah. But yeah, the first thing you think isn't, I found a new fundamental particle. It's, I messed up. Yeah. Okay. Anything else? Okay. Oh.
For right now, if we do have some other questions, I think that we'll excuse some people.
Yeah.
And we can meet in the front for a little bit. But I'd like everybody to thank Anna for giving the talk today. But I'm sure that we could go on for about 7 more hours with questions, especially something like this. If I do have any students that stayed for my class, if you want to come over here and sign in, I said that you could do that at the end and avoid writing the paper. All right, so I'll just have it right over here. So if anybody does want to stay in front here, then you can ask a few more questions. I